Hello, everyone. This is Professor Ma, and this is the talks on the inductions, okay, mathematical inductions. And I want to start with these two pictures. And the reason I want to start with these two pictures is because it gives a flavor of what the mathematical induction is going to be. Okay. And in particular, in regard to these two pictures, if I were to ask you, say, imagine these, for instance, the cactus on the right-hand side, imagine you zoom out, what will it look like? I think most of us can you imagine as it zooms out, you got these layers of spiraling leaves sticks out. Or put it another way, if I were to take a little, so we'll take the centers, say, out the rows and then blow it up, and then realize, wait a minute, that looks basically just look like as before. And the reason that we can retain the patterns and to imagine what these patterns, because we can mentally rebuild what the image is for the next layer, which based on the present layers, and the next layer, and so on, so on. In other words, its propagations, the new ones, is based on the patterns of the old. Okay, and this is what mathematical inductions is about. Mathematical induction is a method we try to verify infinitely many statements. Usually, a lot of times these are formulas. Okay, and in particular, so I'll give you an analogy to the patterns of the rows of the. Okay. Suppose I look at patterns of the following things. I starting playing around with R numbers, 1 equal to 1, and add the first two R numbers, I get 4, which is 2 squared. Okay, and add a third 3 R number, get 9. I get 4 R numbers, get 16. Then here the patterns emerge. Okay, that is not difficult to guess what next pattern is. It says 1 plus 3 plus 5 plus 7 plus 9 is going to be 25, which is of course true. That's good. Okay, and so will this pattern persist? Of course, I can say, yeah, of course it persists. Look, like there's so many of them, they all match up, but the mathematically proof. Mathematical induction is a methodology to establish the true, the trueness of all these infinitely many, you can say, formulas. And the first thing we want to do is write the formula correctly, write the questions correctly. Okay. In other words, write the patterns correctly. And what is the pattern we're saying? We're saying, first of all, in English and descriptions is the sum of n R numbers is n squared. And in mathematics, since R numbers are represented by 2k minus 1, so can I write these in summation notations of 2k minus 1 and add from 1 to whatever n, get n squared. Okay? And so, in other words, this is the pattern I see in these formulas. Okay? In the case of the plants and the flowers, I can use my imaginations and zoom out the picture and imagine what it looks like as it keeps goes on. At infinitum, they all look the same. But in mathematics, we need to do things slightly differently. We want to prove every one of these things is true. Of course, I can now write every one of them out, check every one of them, because there's not enough time in life, right, to do these, the infinite many things that involve. So here is the strategy of the mathematical inductions. Okay. First, we layer the statements out. We say the first statement, which is obvious, okay, but we throw in the groups of the statements we would like to demonstrate, to prove. Okay, and the first statement is 1 by itself, 1 squared. The next statement is 1 plus 3. Adding 2 R numbers, I get 2 squared. Next statement is 1 plus 3 plus 5. Adding 3 numbers, I get 3 squared. And I separate them into statements 1, statement 2, statement 3, and so on and so on. And the statement n is 1 plus 2 plus, so 1 plus 3 plus 5, so on, so on, up to 2n minus 1, I shall get n squared. Okay? I want to justify all these statements for every n, from n starting from 1 to infinity, goes on forever. And how do we do that? Okay, here's a strategy. And the strategy it's very neat. Is the domino effect. Okay, what are you talking about? You will see people line up dominoes, really, really long dominoes, and they just play, mount and mount and go over the face, and then the big moment comes, they roll the drum, and they want to knock down all the dominoes. What do? Tap the first one. The first one falls, it knocks the second one over, the second one falls and keeps going. And we call this the domino effect. So mathematical induction is that. Okay. In the case of dominoes, what do you need to do? Make sure that everything will fall over. Two things. When you line them up, make sure the dominoes are close enough so when one fall over, it will knock next one over, and next one will knock next one over. In other words, they're interconnected. So one will knock next one over. Okay, you have to make sure that your dominoes are set up like that. And the second thing is you have to knock the first domino over. So you will knock the second one over, and so on and so on. The chain reaction will carry on to ad infinitum. Okay. And this is what we're going to do in terms of proving the statements we have before. The sum of first and odd numbers is n squared. Okay. So, and what do? We do the following things. Okay, we first make sure that the first domino gets knocked over. It's true, right? In this case, what I mean by knocking over the domino, we mean that statement is true. Okay. And then the next things we're going to do is we're going to prove that it doesn't matter where you are in between the in the line of dominoes. Okay, you're going to prove that any statement that's true will cause the next statements to be true. Okay, that is the tricky part. It's kind of hard to absorb what's that meant. What meant is that the patterns you have know that up to this point is true. That pattern will help you for the next theorems or the next statements to be true with the help of a previous patterns. So how we do it, let's see. Okay. And mathematical induction is a very formal argument in the sense, if you're going to use arguments for this in mathematics, you have to declare to your readers, say, I'm going to use mathematical induction. Hence, I'm going to check the first case. I'm going to check the case that Sn implies Sn plus 1. Okay? So we'll have to state that. Okay? We're using inductions to prove this. So what we're going to do, we're going to verify the very first statement. What do we mean by first statement? It means that number n is 1. Okay? There's only one number, 1 is 1 squared. Check. So the formula worked. You can plug in 1. Okay. Now, here comes the part which some people kind of hard to digest. We're going to assume this pattern, that is this formula worked up to a point. That is the photo I gave you, the plants. The pattern persists up to this much. Okay. Then we're going to use that to show that the next pattern has to be true because these patterns over here follows the law, follows the formula. Okay, so we're going to assume the formula works up to n. What does that mean? It means adding the first n integer becomes capital N. Okay, so assume that pattern persists. Now I want to show that the formula is also true up to for the next number, n plus 1. What do we mean by that? It means we're going to add 1 plus 3 plus 5 up to here. We're going to add next R number. What's next R number? 2n plus 1. Okay, so in other words, we're going to add one more things to it. So picture's all bigger. One more layer. Okay. Here is where the old pattern is. Up to here. We know that's n squared. So that patterns can be, that sum can be compact or calculated as n squared. So this is why I use this assumption. Okay. Assume this work for up to this point. That is, this part, the part previous part will add up nicely to n squared. And now all I have to do is add these little new things, the 2n plus 1 minus 1, to this n squared. And lo and behold, when you clean it up, this is n plus 1 squared, which is exactly what we want to show. So this is the induction argument. Okay. So two parts, you have to first demonstrate the first statements of the problem is true. Then you have to assume the pattern up to n. Then you have to write out a formula for n plus 1. Okay, then you can show the first, then you apply the induction hypothesis for the first n of them, and plus the new one. Okay, then their patterns will fold into the new, in this case, n plus 1 squared, just what we expected. Okay, so and then here's another example for even proving inequality using induction. Okay, and that's it. This is probably one of the most interesting sections in terms of conceptually for this course. And yeah, it's pretty neat. Yeah, I like it very much. Hope you enjoyed it. And talk to you later. And bye-bye. Doctoring and